One example of a tree data structure that's used very commonly in video games is something called a quad tree. Now, quad trees are in 2 dimensions, and there's also these things called OctTrees, which are used in 3 dimensions. But I'm drawing this on a 2D sheet of paper, so we'll talk about quad trees in this example. Now, quad trees are a way of representing objects inside of your game spatially near one another. So it can help speed up doing really quick queries on what is nearby me, or give me the list of all of the targets or all of my enemies in one given area. And I'll show you exactly how that looks. So if you imagine this whole sheet of paper as our game world, and we have a whole bunch of people running around inside of it at various locations, right? You could think of this as a really large MMO or some sort of RPG game. And maybe there's some big clusters of people over here and some really sparse areas. You could think of maybe these are where the cities are inside of this big game. And we have this big MMO or open world RPG game or something else along those lines. Now, one common thing that could happen is if I'm standing at this position and I use some sort of area of effect spell that's supposed to target everything around me. Well, the question is, well, who's around me? Which of these enemies, these potential targets, do I need to possibly hit? Now, one way that you might go about doing this is saying, well, I'm going to iterate through my list of all enemies in my entire game world and see which ones are close enough to this given position. Now, this ends up being like a linear time function where you're essentially iterating through each one of these enemies, each one of these potential targets throughout your entire game world. And this can be okay for a lot of smaller games, a lot of games where it's just you and 5 or 6 enemies on the screen, and that's it. But once you're talking about something really big, like an MMO or an open world RPG, these X's may be hundreds and hundreds of different enemies. So it can very quickly get very time consuming to do all these distance checks to determine which ones are nearby. And the interesting thing is your grenade may only have some sort of area effect that's sort of this big, and you're still doing distance checks against these enemies out here, which are obviously too far away. So one way that we can sort of split up this world is into something called quad trees. And quad trees spatially divide this entire area up into a tree-like data structure. So if you imagine we take our entire game world and we just encompass this entire thing inside of a box, right? This essentially is our root node, right? It contains everything in the entire game. And then we split this thing into 4 different sections. And we'll just do it like this. And for any of these potential targets that may be on the line, they're going to be on one side or the other, right? There's no one who's perfectly on a line like this, right? Now, what we have so far is we have this giant box. I'm going to call it A. And then we have these 4 boxes inside of it. B, C, D, and E. This structure so far, where B, C, D, and E are all inside of A, could be represented by a tree data structure like this. Here's our node A, and then underneath this, we have 4 child nodes, B, C, D, and E. Just like this. Now, each of these, this is how we get that quad tree, right? Because each of them have 4 children. Now, each of these spaces could be further subdivided into 4 other smaller components, right? I'm just going to do it on this area here because it's the only one that we really care about for this example, right? So B, C, D, E, and then this might be F, G, H, and I. So inside of E is F, G, H, and I. Inside of E, so inside this node here is F, G, H, and I, right? These are 4 nodes that are underneath my node E. So the interesting thing about this is if I have an enemy at this position here who's in this box F, well, they're in this node here, F. And F is also inside of E. And E is also inside of A. So if I were to query to my game space saying, give me all the enemies that are inside of A, I'd be querying, give me all the enemies that are inside this entire space. If I said, give me all the enemies that are inside of F, I'm only querying this tiny little box down here, right? So I'm subdividing this space out into these smaller and smaller quad trees. Now, in this example here, if I have a grenade and it has this area that's about this size, right? We can say, okay, it overlaps D a tiny bit, right? We could say that this space here is larger than H. So instead of looking at just H, which is where the grenade went off, we could instead look at E, right? And E contains F, G, H, and I, right? So by looking at this box E, we're looking at this entire space. And then, because I have this slight overlap here, we may also look at E as well as D, right? So already we've split our game world in half, right? We don't have to do any of the queries in this space. So essentially we'd have this tree data structure that looks something like this. Each of these are representing a logical space inside of inside of our large 2D game world. And then in each of these nodes, in each of these leaf nodes, is where our enemies are sort of contained. We contain references to all the enemies that are inside of F and all the enemies that are inside of G, all of them are inside of H. And it allows us to very quickly do these sort of queries. To give you one more example, if I then threw a grenade, somewhere up here in this space, right? Well, this space up here, B, could be subdivided into 4 small areas. And if this is like a really, really small grenade, I can even further subdivide this into smaller spaces, right? And now, if I have this really small distance check that I'm doing here, instead of doing a huge check against every single enemy in my entire game, I could just check these 2 boxes up here, these 2 spaces here, right? These 2 would be encompassed by this space here. This space would be encompassed by B. So the spaces that we're talking about here is actually a child of B. There'd be 4 nodes inside B, and then under one of those nodes, there'd be 4 nodes inside that, and we'd just be looking at 2 of them. That is what a quad tree is. OctTrees are this exact same approach, except in 3 dimensions. So you can imagine these things as cubes, and you're subdividing it into 8 internal cubes, right? It would kind of look like, if I have a really bad 3D drawing here, I can give it a shot though, right? And then you subdivide this thing into, let's see, how would I draw this? Subdivide this thing into multiple smaller spaces, kind of like that, I guess, right? Where you actually are splitting this thing up into 8 different 3D cubes in the exact same way that quad trees work. And then you can split each of those into smaller spaces, into smaller spaces, into smaller spaces. This gives you some really good optimizations whenever you're doing sort of these spatial queries. And this idea of quad trees and OctTrees is actually used in a lot of the physics simulations that you are probably already used to using.